Hi, in this video I'm going to talk to you about what's going on in the probability homework and some advice for how to complete things. If you process the homework 2 probability file or look at the processed version, you'll see that the first problem talks about a chimp who is faced with a computer screen and the numbers 1 to 7 appear randomly on the screen all at once, and then the chimp touches the numbers in the right order, and every time a number is touched it disappears off the touch screen. And so the question is, what's the probability that the chimp I will touch the number 1 first, and then number 2, and then number 3, and then 4, 5, 6, and 7 in the right order? Remembering that every time the chimp touches a number, the number that's touched goes away. I would suggest solving this problem in terms of a tree problem. First branch of the tree is something like choosing number 1 or not choosing number 1. Given that the chimp is choosing randomly, what's the probability that the chimp would choose a 1? And then in the next set of branches, what's the probability that the chimp chooses 2 or not 2, keeping in mind that after the chimp has touched 1 it goes away. And that should give you a cascading tree diagram where you can figure out the probability of this sequence. In problem 2, we know a probability distribution for milk chocolate M&Ms, and we know the probabilities of all the colors except for blue, and we should be able to realize that probability distributions have outcomes that sum to a total probability of 1. So therefore you should be able to add up the probabilities for all the other colors and subtract that probability from 1, and that should give you the probability of blue. In part B, problem 2, you're supposed to find the probability of selecting a candy that is not a primary color. So add up all the probabilities for the non-primary colors. Please note that primary colors are blue, yellow, and red. In problem 3, you're asked about what's the probability that a roulette ball would land in slot number 22 on the wheel. You're told that a roulette wheel has got 38 slots. You're to presume that all of the positions are equally likely. So what is the probability that the ball will land in one of them? Hopefully you can figure that out from our basic principles. Die tosses, coin tosses. This would be equivalent to flipping or rolling a 38-sided die. What's the probability it lands on any one side? In part B, you want to know the probability of winning on green. If you bet on green, what's the probability you win? You need to take the total number of green places divided by the total number of places on the wheel, which are 38, and that should give you the probability. In part C, 3C, you're supposed to find the probability of winning on a column bet. I would go in the notes to the overhead that contains the betting board for roulette and count up the number of numbers that are in a column, and that should be your numerator of this probability, and the denominator of the probability would be the total number of places on the roulette wheel total, which would be 38. In problem 4, you need to find the total number of ways that you can arrange the digits 4, 5, and 6, and find out how many arrangements that is, because that's the number of ways you can win, and then divide that number by 1,000 arrangements, because there's 1,000 arrangements of 3 digits. So it should be the number of ways you win divided by the possible number, which is 1,000. Do the same thing on part B. In problem 5, you are told about a theft insurance system where this particular vehicle has 21.6 theft claims for every 1,000 that are insured. That's a probability of 21.6 divided by 1,000 for the probability of a claim. The probability of no claim on a vehicle would be 1 minus that. And so I've created a chance list right here which has the probability of no theft claim in the first position and then the probability of a theft claim in the second position. The loss to the insurance company, or the payout or the benefit, is $0 in the first position if there is no vehicle theft. And if there is a vehicle theft, we figure on about $10,676 given in the problem. So this is the value of the random variable, what we've been calling x in class. And x has two values, 0 and 10,676. The probability list is called chance, and to find the expected vehicle claim amount, you need to multiply the losses times the chances and add them, make a list of products like I did here under the product list. And then to find expected value, you sum the elements of that product list to get an expected outlay by the insurance company of $230.60 per policy. The question asks you in part A, how much does the insurance company need to charge to break even? So if they are paying out about $230.60 per policy, hopefully you can figure out how much they have to charge to make a break-even point. In problem 6, we have a Wisconsin lottery game, and we're told the probabilities of all the different outcomes except for the probability of losing and winning $0. That part has been left off, and again we'll figure it out by adding the probabilities together that we do know and subtracting from 1. I'm doing that right here in the code block for the missing. The missing computation takes all the probabilities that are given, adds them up, and subtracts from 1. And that is computed right here, so it looks like it's about 0.7793. And in part A, it asks what is the probability that the player loses the game. You just simply need to copy this probability from here and paste it in here for the answer. That's your probability of losing the game, not winning anything. In part B, what is the expected net gain for a player that plays this game once? Keeping in mind that the cost of the game is $1. I think it said that right in problem 6. It costs $1 to play it. So we need to find the expected payoff, the expected payout of the game. And to find the expected payout, we need to take the amounts that we can win, the random variable values right here, 0, $1, $2, $3, 18, 50, 150, and 900. Those are the different amounts that can be won. And we have found the probabilities because we were given some of them into this list, and then we tack on the part that was missing onto the front of it, and so we get a probability list that's right here for all the different outcomes. Remember, to find expected amount 1, you need to take the product of the amounts times their chances. Here's that product vector. We sum up the values in it, and this is the expected amount that we would win from playing the game once. That is this value right here, the expected amount 1. That is $0.60139 dollars. So the expected net gain is found by taking this expected winnings and subtracting off the $1 cost of the game. And you ought to be getting a negative number for that. In part C, we're asked about playing the game 3 times. And what's the probability the player loses the game twice? Well, this is a probability system with 3 stages, 1 for each play. And so it would be wise of you to construct a 3-layer tree diagram. The first set of branches for the first play, the second set of branches for the second play, and then the third set for the third play. You've seen a tree like this in the notes when we did a 3-question multiple choice exam. Instead of getting it right or wrong, you can win or lose. The probability of losing was decided right here. It's 0.7793. So the probability of winning something is 1 minus that. And hopefully you should be able to fill in the winning and losing tree branches using that information, and then using the tree to find out the total probability for all the outcomes where a player would lose twice. So you're going to have to work out the tree, find out all of the branch paths where you lose the game twice after playing it 3 times, and then totaling up the final probability, multiplying by the branch probabilities for finding all of those. In problem 7, we have a life insurance problem where we are going to sell a life insurance policy to a 25-year-old man, and it's for 5 years of life insurance. We are told that the probability that a 25-year-old would die during the first year of the policy to be this probability, 0.00039. The probability that someone would die the next year would be this probability. The probability of somebody living up to that point and then dying the next year when they're 27 would be this probability, and so forth. So we have the probabilities of dying in each of the remaining years, and we add up all of those probabilities in this first code block, and they total 0.99749. So therefore the probability that well, actually the probabilities total something less, and then if we subtract that from 1, this 0.99749 is the probability that the person lives through the end of the insurance period. And so 1 minus this would be the probability of dying at some point during the insurance period. So what's the probability in A that the man does not die? Well, it's this probability given at the end of this code block, 0.99749. In part B, you are asked to find the expected profit for this insurance policy. And so the first possible outcome is that the man dies the first year. And as I explain here, the profit is listed here as negative $99,825. Well, where does that come from? It comes from the fact that if the person dies, the insurance company's got to pay out $100,000. And so that's the negative $100,000 part of this number. But remember that because it's life insurance, the person had to pay a premium of $175. So if you take $100,000 or a negative $100,000 and you add a positive $175 to it, you get a negative $99,825 profit. In other words, they lose this much money on that outcome. The next year, if he dies, they again lose $100,000 to the beneficiary, but they will have taken in 2 premiums, one premium for the previous year and one premium for the year where he dies. And so that gives a profit that is also a negative number, but it's a little bit different, negative $99,650. And that's where all these negative 99,000 things come from. If he lives to the end of the insurance period, that is also a possibility. If that happens, the insurance company makes $875. Why? Because there was a $175 premium in each of the 5 periods. And that totals a grand total of a positive $875. So these profit amounts are the values of the random variable x. The probabilities for each of these have been determined. The probability that he lives to the end, of course, is this 99749 you figured out earlier. The probability that he dies in this year and gets this, the insurance company gets this negative profit, is this probability right here. And I've made those lists in the code blocks. Here is the profit amounts. Here are their respective chances by putting together the given chances and the part that I computed. And to find the expected profit, you have to multiply the profits times their chances and put in this products list like I did, and then sum up the products. Here is the expected profit for one life insurance policy of this nature for a 25-year-old man, and this value right here that's given is the expected profit. Notice that it's a positive number. We expect that the insurance company is going to make money on this life insurance policy. Even though there could be very catastrophic amounts if he dies, a lot of big negative numbers facing the insurance company if that happens. It's just they're not very likely, and they're weighted by very small probabilities of happening. Whereas this positive number is getting weighted by a very big positive probability, and so it is driving the overall computation to be a positive profit. Problem 8 is like conditional count probability problems that we did in class. What's the probability that you choose a passenger out of the 2,201 passengers on the Titanic? What's the probability that somebody is a female? Well, take the number of females divided by the total number of passengers, and that's the probability of randomly drawing a female. And in part B, what's the probability somebody survived given female? So that's a conditional probability. I would go into all the females and find the probability that somebody survives, or use the conditional probability formula to do that one. Here is a slightly different conditional probability in part C. What's the probability of female given somebody survived? So if I was doing it, I'd go into all the survivors and find out the fraction of them that were females. In part D, I ask you about independence of the events female and surviving. Remember from the class lecture and notes that in order to verify or check on this, you need to calculate the conditional probability of female given survived, and if it matches the probability of choosing a female, then the events are independent. It's pretty intuitive. If knowing the survival information doesn't change your opinion or probability about being a female passenger, surviving is an independent or unrelated piece of information, and surviving and female would be considered independent in that case. If these probabilities, when you calculate them, are not equal, then the events are dependent. So follow the example in the notes for doing this and carry that out right here for this answer. Problem 9 is a tree problem. The description here is that we have a spouse, Jason, who is a cystic fibrosis carrier, and Julianne has a brother. His spouse, his partner, Julianne, has a brother with cystic fibrosis, which means that there's a chance of 2/3 that she's also a carrier. We go through the conditional probability information about whether she can have a child with cystic fibrosis, given that she's a carrier, and so forth. And what I ultimately want you to figure out is the conditional probability that she is a carrier, given that she has a child that does not have CF, cystic fibrosis complement. In other words, a child without cystic fibrosis. You will need to use the conditional probability formula A given B from the notes. You're going to need to construct a tree diagram where, one of the branches is going to be about Julianne being a carrier. The other branches are going to be about whether the child does or does not have cystic fibrosis. And you're going to need to fill out the tree diagram and use it to calculate this conditional probability. I would suggest you follow the HIV blood screening example that is in the notes. That would be very helpful to do this one. and good luck on your homework. Let me know if you have questions.